Moment distribution can be a very effective tool for analyzing indeterminate rigid frames, frames whose connections are all fixed. But to do so, we must distinguish between frames that sidesway and frames that cannot sidesway, because it affects the approach we use. In the case of this problem, we will analyze an indeterminate frame that cannot sidesway, and we'll use moment distribution. The key concepts we'll use are determining fixed end moments and applying moment distribution to predict moments inside frame members. And here is our frame. It's pinned at A, fixed at C, there is a roller at D, and a cantilevered end out toward E. We're given the moment of inertia and modulus elasticity for each of the members, and they're all the same. And we're going to construct the moment diagram for the girder ABDE. To do so, we'll use the following approach. We'll start by approximating part of the answer. So that we can have a way to evaluate the reasonableness of our results. And in the case of this, we'll approximate the vertical support reactions. To begin moment distribution, we'll need the stiffness and distribution factors. And we'll use the modified stiffness factors wherever possible to abbreviate the process. Third step will be to find the fixed end forces, or fixed end moments. Then we'll be ready to apply moment distribution. With that information, the moments within the, at the end of moment distribution, we'll be ready to find the moments in the frame. With that information, we'll be able to find the support reactions. And then we'll compare these support reactions with our approximate answer. That way we'll be able to judge the reasonableness of our results before we construct our diagrams. And we'll construct our shear diagram and integrate it to get our moment diagram. Now I will point out, we could just use the moments we get from the end of the moment distribution process, step 5, and construct a moment diagram. But we lose our ability to ensure that we have a reasonable result. We lose our checks in the process. So we'll go ahead and calculate the support reactions, and we'll use integration to construct the shear and then the moment diagram. And by taking that slightly longer approach, we'll have a much better degree of confidence that we have reasonably created the moment diagram. So let's begin by approximating the vertical support reactions. So we'll focus on just those. And to do so, to make that approximation, we're going to assume that distributed load goes to the nearest vertical support to be carried. Now for this load at the end of the cantilevered end, we're going to assume that the concentrated load goes to the nearest support since it's cantilevered. And the reason why I specify because it's cantilevered, if it was a point load in between two supported ends, then we would assume the distribution was similar to a simply supported member, and it's inversely proportionate to the distance to the nearest support, or to the distance to the supports. So based on the assumptions we are making in this problem, AY will be approximately, if we take a look, we see that there are 7.5 feet going toward A, 7.5 feet going toward B from this side, 6 feet going toward B from that side, and 6 feet going toward D there. So we have the 2 kip per linear foot distributed load, 7.5 feet of it going toward A, and we get 15 kips acting up. CY down here, in essence supporting point B, we'll have 2 kips per foot, the 7.5 from the left, the 6 feet from the right. Put those together and we'll predict roughly 27 kips acting up at point C. And dy will be approximately the 2 kips per linear foot acting over the 6 feet from the left side, and that cantilevered load, the 8 kips. Put those together and we'll predict roughly 20 kips acting up at D. Now to begin the moment distribution method, and to do so we need to find the stiffness and distribution factors. So let's start with bending stiffness. First thing I want to point out, EI is constant for all members. So rather than plug in the numbers that we have, I'm going to leave it as a constant for as long as I can. Now, since member AB is pinned on one end, continuous on the other, we can use the modified stiffness of 3 EI over the length, which is 15 feet. And there will be no carryover from node B to node A in member AB. Now, since the ends of BC and BD are fixed or continuous, we'll use our traditional bending stiffness So for member BC, it is 4 EI over the length, which is 12 feet. And for member BD, it is 4 EI over the length, which is also 12 feet. Now, you'll notice that we've not calculated stiffness for member DE, and that's because it's cantilevered. When node D gets released, member DE has no stiffness to draw moment, and so we just won't calculate it. So now we're ready to find the distribution factors. The distribution factor for node A of member AB is 1 because it's pinned, but I'll point out we're not going to use this because we're using the modified stiffness for member AB, and so there'll be no carryover and no fixed end moment at node A. At node C of member CB, the stiffness is 0 because it's a fixed support. The distribution factor at node D and to member DB is 1 because we said the stiffness of member DE, the cantilevered end, is 0. So we could have written that out longhand, but we'll just take the shortcut and note the stiffness, the distribution factors. Now node B. To figure out the distribution factor at this node, we need to sum the stiffness of all of the elements meeting at this node. So we have member BA, member BC, and member BD, which have stiffnesses of 3 EI over 15 feet plus 4 EI over 12 feet plus 4 EI over 12 feet, and the least common denominator will be 15. When we modify the numerators, add them all up, we get 13 EI over 15 feet. So to find the distribution factor, the portion of unbalanced moment that goes back into member BA, we take the stiffness of member BA divided by the sum of all the stiffnesses at that node. We have 3 EI over 15 feet divided by 13 EI over 15 feet. The EI's cancel, the 15's cancel. The 3 over 13 is 0.231. Distribution factor for member BC. The stiffness for member BC over the sum of all the stiffnesses at that node, we have 4 EI over 12 feet divided by 13 EI over 15 feet, and that gives us 0.385. And then the distribution factor for member BD is the stiffness of member BD over the summation for all of the stiffnesses at that node, and it's exactly the same as the previous 4 EI over 12 feet divided by 13 EI over 15 feet, so it is 0.385. Now if we've done this properly, the three stiffnesses, or the three distribution factors, should all add up to 1, and their summation to within round off, not 0, equals 1.0. So even though there's a slight rounding error, that should be good enough, and we're ready to move to the next step. Now we need to find the fixed end forces. Let's start with member AB. In this case, we have a pin support, or we'll idealize as a roller at one end, fixed at the other, uniform distributed load. Draw the moment clockwise. We find this situation inside the back cover of our text, and it looks like this, where the moment is omega L squared over 8, and it is down at the back end. So the fixed end moment, AB, being down at the fixed end, is the way we drew it when we drew it clockwise. So it's a positive omega L squared over 8. It's 2 kips per linear foot. Times 15 feet squared over 8 gives us a positive 56.25 foot kips clockwise, as the way we drew it. Now for member BD. By the way, we don't have a fixed end moment at A. We're going to use the modified stiffness for this member, so we consider that a roller, and clearly the moment is 0 at the roller end. But for BD, we're going to get the fixed end moments by considering it fixed, uniformly loaded, and that is this situation. So we have omega L squared over 12 is the moment at each end, but at the left end it's counterclockwise. So the fixed end moment, BD, is going to be a negative omega L squared over 12, and that equals minus 2 kips per linear foot times the 12-foot length squared over 12, and that equals a minus 24 foot kips, where clockwise is positive. And at the other end, it's a positive omega L squared over 12, and that's positive 24 foot kips. Now for member BC, and I'll turn it on its side so that it will resemble the situations we have in the inside back cover of our text, but there's no load applied in between. So the fixed end moment BC is 0, and the fixed end moment CB is 0. Now for member DE. In this case, it's cantilevered out with a concentrated force at the end. So our fixed end moment, DE, is the cantilever moment minus PL. So that equals minus the 8 kips times the 8 feet, and that gives us a minus 64 foot kips. It is not clockwise. And if I draw these up on our picture of the structure, with labels. This is the fixed end moment in member BA. This is the fixed end moment at the top of member BC. Fixed end moment at the bottom of member BC, and both of those turned out to be 0. Fixed end moment at the left side of BD. Fixed end moment at the right side of BD. And the fixed end moment at the end of the cantilever, DE. Oops, I made a notation error. We see here that the fixed end moment for member AB is only at the B end, and I mislabeled this one. It should be fixed end moment BA, because the fixed end moment at A is 0. Now we're ready for step 4, where we apply moment distribution. So I've created a worksheet where each of the nodes or joints are listed, along with each member framing into that node. And we need to input the distribution factors for node A. We said it would be 1. CB, we said it would be 0. DB, 1, and DE, 0. And for node B, we said the distribution factors would look as so. .231, 0.385, and 0.385. Now everything below this line will be a moment with units of foot kips. But to keep the worksheet from becoming too cluttered, I won't write the units. Now to find the fixed end moments. And let's start at node A. We saw previously there is no fixed end moment at A because we are using the modified stiffness and noting that A is pinned. And since there will be no carryover from the node B side of member BA, this node will not receive any moment during moment distribution. But now, for the members that frame into node B, BA has a fixed end moment of 56.25 foot kips. BC we found to be 0. And BD we found to be negative 24 foot kips. Now at node D, in member DB, the fixed end moment was a positive 24 foot kips. And at the DE end, we said the moment holding up the cantilever is a minus 64 foot kips. And at the bottom support, node C, we had 0 fixed end moment. Now we're ready to release our first node. And because node A carries no fixed end moment, there's no need for us to release node A. So let's jump to node B. We're going to need to take the opposite of the unbalanced moment, and the unbalanced moment is the 56.25 plus the 0 minus 24, and that equals a minus 32.25 foot kips. And this is the quantity we need to distribute to the three members framing in at node B. So when I take 0.231 times this moment we need to distribute, we get a minus 7.45. When I take 0.385 times this moment we need to distribute, I get a minus 12.42. And since this is the same distribution factor, we get another minus 12.42. I will underline these three quantities because at this point now, when I clamp node B again, node B is in equilibrium. But we have moments that carry over. Now I want you to note that nothing carries over from the B end of member AB. We use the modified stiffness reflecting that node A is a roller. So there'll be no carryover from this end, but from B to C, we'll take half of the minus 12.42 and it carries over, and that's a minus 6.21. And likewise from B to D, we get a carryover of minus 6.21. Now to release another node. Well, there's no need to release node C. Its distribution factor is 0. It's the fixed support. So all moment that is distributed to node C goes into the fixed support, and none of it gets distributed back into member BC. So let's jump to node D. Need to reverse or take the opposite of the unbalanced moment, and the unbalanced moment is given by 24 minus 64 minus 6.21. Take the opposite sign of all of that, and we get 46.21 foot kips needs to be distributed. And so we take this quantity times we take this quantity times the distribution factor 1, and we get 46.21 goes into member DB. None of it goes out into the cantilevered end, and now node D is in equilibrium. We clamp it back down, but there is carryover to the other end of member DB, and so half of the 46.21, which we will round off to 23.10, carries over to the B end of member BD. We won't get any moment at node A in this process, so we don't need to release node A. We won't get anything distributed back at node C, so we don't need to release C. So let's go back to node B. And the unbalanced moment is the 23.10. When we reverse the sign, we get a negative 23.10 foot kips. We take that quantity times 0.231, and we distribute a minus 5.34 to member BA. We take the minus 23.1 foot kips times 0.385, and we distribute a minus 8.89 foot kips to member BC, and a minus 8.89 foot kips to member BD. And now node B is in equilibrium. We clamp it back down. There is carryover, in some of the members, not to A, but we do get some carrying over here, and this is half of 8.89, which we will round off to a negative 4.44, and half of this one comes out to node C. We'll round off at a negative 4.44. So now we release D, and we'll keep going back and forth between those two nodes in this case. Our unbalanced moment is just the negative 4.44, because if we add all of these up we get 0, and so it's only this one that's unbalanced, and we get a positive 4.44 that must be distributed. But my distribution factor is 1, and it all comes back into member DB. And so node D is once again in equilibrium. We clamp it back down, but we get carryover to the B end of the member, and half of 4.44 is 2.22 foot kips that carries over. And now we release node B, have a minus the 2.22 foot kips, which gives me a negative 2.22 foot kips to distribute, and I take that quantity times the 0.231, and we distribute a negative 0.51 foot kips to member BA. I take this quantity times the distribution factor, and I distribute a negative 0.86 foot kips to member BC. And I take this quantity times the distribution factor, and I distribute a negative 0.86 to member BD. Then I clamp down that node. Once again, it is in equilibrium, but I have carryover. None to A, but to the other end of member BD, I carry over a negative 0.43, and to the other end of member BC, a negative 0.43 foot kips. An important question is, when do we stop? I typically prefer to continue this iterative process until my unbalanced moment at any node, at all nodes, is less than about 1% of the fixed end moments we started with. And so we had a 56 and a 64 and a 24, so I'm going to shoot for an unbalanced moment of less than about 0.2 foot kips, and then we'll stop. So let's release node D. My unbalanced moment is a negative 0.43 foot kips, this one. And so when I reverse the sign, I need to distribute a 0.43 foot kips. The distribution factor is 1. It all comes into the member DB. None of it goes into the cantilever member DE. And that node is in equilibrium. Let's carry it over to the other side of the member BD, and we distribute a 0.22 is what we'll round that off to. So one more time, I'm going to release B. My unbalanced moment is 0.22 foot kips, and so we'll put a negative sign in front of that, and we'll distribute it according to our distribution factors, and I'll get a negative 0.05. When I use this distribution factor, I get a negative 0.08, and for this one a negative 0.08. This node is now in equilibrium, And if we carry over our distribution, or if we carry over to the other ends of member BC and BD, we're carrying over something well below the 1% I was looking for, and so we'll stop the iterations at this point, which means we're ready for step 5, which is to find the moments in the frame. And so I add up all the quantities in one column, starting at the fixed end moment and down. And so there is no moment at the pin A. Good, that's to be expected. We take 56.25, subtract 7.45, subtract 5.34, subtract 0.51, subtract 0.05, and we get a positive 42.95. For member BC at node B, we add these up, the 0, the negative 12, the negative 8, the negative 0.86, negative 0.08. Add all those up in our calculator, we get a negative 22.25 foot kips. And come to member BD, add each of these together, and I get a negative 20.71 foot kips. Now I want to point out, at node B, it should be in equilibrium, which means the sum of all of these three should equal 0. We get a negative 0.01 foot kips, which is sufficiently close to 0 for us, and so that satisfies equilibrium. That's a good sign that we did not make a math error along the way. We now go to member DB, the 24, the minus 6.21, the positive 46.21, and these add up 0 and these add 0. Add those all together and we get a positive 64.0 foot kips. For member DE, the cantilevered member, there's the negative 64 we started with, nothing else, so a negative 64.0 foot kips. Again, everything framing into node D should add to 0, and it does. That's a good sign. Then the fixed support at node C. We have a 0, minus the 6.21, minus 4.44, minus 0.43. All of those add to a negative 11.08 foot kips. And I will darken this line so that we recognize this bottom row of numbers as our final predictions of moments in the frame. Now we're ready to find the support reactions. And we'll start with member AB, which is 15 feet long, has a vertical reaction at A, distributed load of 2 kips per linear foot, unknown shear just to the left of point B, and a moment MBA, which we found to be a positive 42.95 foot kips. So let's sum moments about point B, and I'm going to choose clockwise as positive for my summation. The choice is mine, but since we draw our moments clockwise in moment distribution, that's my choice. I get a positive contribution from reaction AY acting through 15 feet, a negative contribution from the distributed load acting over 15 feet, which gives me a resultant, and that resultant acts 15 over 2 feet from point B, and we have the moment at the cut, 42.95 foot kips. Put all of that together and we get an AY of positive 12.1 kips, so it is up. Then I sum forces in the Y direction. I have the 12.1 kips vertical reaction at A minus the 2 kip per linear foot acting over 15 feet and a negative contribution from the shear just to the left of B. So the shear just to the left of B is a minus 17.9 kips, and my sign convention for shear is such that it spins the piece clockwise, so it depends on which side of the cut we're looking. Now, free body diagram of member BD. And this one's a little shorter. This one is 12 feet long. Has uniform distributed load of 2 kips per linear foot, an unknown shear to the left of point D, an unknown shear just to the right of point B, moment BD we found to be negative 20.71 foot kips, and the moment at the other end, DB, we found to be a positive 64 foot kips. So I will sum moments about point D. Again, I will choose clockwise as positive. I get a positive contribution but a negative magnitude from the moment at the left end, moment BR. I get a positive contribution from the unknown shear just to the right of B, acting through 12 feet, a negative contribution from the distributed load acting over 12 feet, and its resultant acting at 12 over 2 feet from B, and a positive contribution from the moment at D. I solve all of this for the moment just to the right of B, or the shear just to the right of B, excuse me. We get a positive 8.4 kips using our standard sign convention for positive internal shear. And then I'll sum forces in the vertical direction. I will choose up to be positive. I get a positive contribution from the shear just to the right of B, a negative contribution from the 2 kips per linear foot acting over 12 feet, and a negative contribution from the shear just to the left of D. If I solve that for the shear just to the left of D, I get a negative 15.6 kips with my standard sign convention for positive shear. Now we move to member DE, the cantilevered element of the frame. It is 8 feet long, has a concentrated force on the end, an unknown shear to the right of point D, and a moment we found to be negative 64 foot kips. And I will apply vertical equilibrium. Choose up to be positive. I have my unknown shear to the right of D, minus the 8 kips applied concentrated force. The shear to the right of D is a positive 8 kips using our standard sign convention. Now let's move down to member BC. We have the member, which is 12 feet long, an unknown vertical reaction CY, a moment reaction that we calculated, MCB. We have a shear just to the right of point B, which we found to be a positive 8.4 kips. A moment, BD, a shear just to the left of point B, which we found to be negative 17.9 kips, and a moment, BA. We know all of these moments, but there's no need for me to write them in order to apply vertical equilibrium. I get a negative 17.9 kips plus the vertical reaction CY minus an 8.4 kips shear at point B. Put those together and I get CY as a positive 26.3 kips. It is indeed up. Now to get the vertical reaction at D, we're going to draw a free body diagram of an infinitely short piece at D. So short that the distributed load coming between B and D acts over too small of a distance to contribute, and so short a distance that the shears don't contribute moment. We have the shear just to the left of D, which we found to be negative 15.6 kips. And just to the right of D, we found to be a positive 8 kips. We have the moment, DE, and the moment, DB, both drawn counterclockwise, because we always draw our moments clockwise in moment distribution when they're on the ends of the frame members or frame elements. Newton's third law says that on the node they have to act equal and opposite so that they are counterclockwise. But I don't need their magnitudes in order to apply vertical equilibrium. I get a negative 15.6 kips contribution from the shear to the left, vertical reaction at D, and a negative 8 kips contribution from the shear at the right. dy is a positive 23.6 kips, and it is up. Now for step 7, where we will compare our vertical reactions or our support reactions with our approximations. and we had approximated AY, CY, and DY. And we predicted them to be roughly 15 kips, 27 kips, and 20 kips, all acting up. And from moment distribution, we found AY to be 12.1 kips up, CY to be 26.3 kips up, and DY to be 23.6 kips up. And when we compare these magnitudes, we find them reasonably close, so that we will say that our moment distribution results are reasonable. So now I'm ready to construct the diagrams. Let's start with the shear diagram in units of kips. We saw that at end A, the vertical reaction causes a jump of 12.1 kips, then we have a uniform distributed load, so the shear diagram will be linear and decreasing, and will decrease until point B, where its new magnitude will be the 12.1 kips we started with minus the 2 kips per linear foot acting over 15 feet, and that gives us a shear of minus 17.9 kips, which matches our prediction. That's good assurance. We then have the vertical reaction at C causing a jump of 26.3 kips. So we had a negative 17.9, and we had a positive jump of 26.3. Therefore, our shear becomes 8.4 kips just to the right of point B, which is also consistent with what we calculated previously. That is a good intermediate check. Then again, we have uniform distributed load, so we have linearly decreasing shear diagram until it reaches point D, where we have the 8.4 minus the 2 kips per foot times the 12 feet gives us a shear of negative 15.6 kips just to the left of D, which is consistent with what we calculated previously. Then we have the vertical jump at D equal to 23.6 kips. So we had the negative 15.6 plus the 23.6, and that gives us a net of positive 8 kips at D, just to the right of D, which again matches our previous calculations. And then we have no applied load, so the shear must be constant until we reach point E, and then we have the 8 kips shear minus the 8 kips applied concentrated force, which leaves us with 0 at the end. It should close to 0. So these are indications that we have reasonably constructed the shear diagram. Now the moment diagram. This will be in units of foot kips. To be able to integrate the shear diagram to find the moment diagram, I'm going to need to know two distances. And I'll label those x1 and x2. And we'll get those from similar triangles. I know that the ratio of x1 over the height of the shear diagram at this end has got to be the same as the full 15 feet divided by this height plus this height, in essence looking at and comparing it to this triangle. And if I solve that for x1, I get 6.05 feet, which means this portion is 8.95 feet. Now for x2, the ratio of x2 to 8.4 kips will be the same as, for this triangle, the base of 12 feet over the 8.4 plus 15.6. Solve that and I get x2 is equal to 4.2 feet, which means that this portion is 7.8 feet. So now to begin constructing our moment diagram. We know that at the pinned end A, the moment starts out at 0. We have a linear shear diagram, so we'll have a quadratic moment diagram starting with an initially positive slope that gradually decreases to 0, so we'll reach a relative maximum positive moment here at this point, and then it will decrease and become negative to that point. So our moment diagram will look something like that initially, and the value at this point will be the integral of the area under this part of the shear diagram, which is 1/2 times the 12.1 kips times the 6.05 feet at x1, or 2x1, and that gives us a moment of 36.6 foot kips. Then as it continues on, we start out with the 36.6 foot kips and we add the integral of this area, which is 1/2 times the minus 17.9 kips times the 8.95 feet, and that gives us a moment of minus 43.5 foot kips, which is only slightly different than the 42.95 we had predicted from moment distribution, and that difference could reasonably be due to round-off error. Then at this point we get a jump in the moment diagram due to the moment from member BC, and that moment is 22.25 foot kips counterclockwise on the end of member BC, which means it's clockwise applied to member ABD, and a clockwise moment applied to a member is a positive jump in the moment diagram. And so we'll round that off to 22.2, which means we reach a negative 21.3 foot kips just to the right of node B, so MBD, which again is fairly close to what we had predicted through moment distribution. From here, the moment diagram becomes quadratic again, with increasing slope to this point and then decreasing slope. And if we take a look, the value at this point is the minus 21.3. Then we add the integral of this area of shear, which is 1/2 times the 8.4 times the distance 4.2 feet. And so this quantity is a minus 3.7 foot kips. Then it becomes increasingly negative, and we had a negative 3.7 foot kips, and we add the integral of this negative area of shear, the 1/2, negative 15.6 times the 7.8 feet, and all of that equals a minus 64.5 foot kips at node D, which again is very close to what we had in moment distribution. And then from this point we integrate the shear diagram, which is constant, so we have a linear moment diagram, and its new magnitude, we had the minus 64.5 plus the 8 kips through 8 feet, which gives a negative 0.5, which is pretty close to 0, so it closes, and that's a good sign. So our approximate analysis suggested that the support reactions we calculated after performing moment distribution were reasonable. Then we integrated distributed load to get the shear diagram and found those shear values to match our calculated shear values when we were calculating support reactions. We integrated the shear diagram to get the moment diagram, and to within a reasonable amount of round-off error, that matched the values we obtained from moment distribution. So we have reason to believe that we have a quality moment diagram for this indeterminate beam ABDE. Now let's go back and review the process we followed to construct this moment diagram. We started by approximating the vertical reactions, and we said that distributed load goes to the nearest vertical support, and that the applied load at the end of the cantilever would go to its nearest support. We then calculated the bending stiffness for each member, and we noted that member BA can be represented as fixed on one end, pinned on the other, and we used the modified stiffness, which also means that we did not need to have any carryover from B to A or any moments, fixed end moments calculated for point A. We then calculated the distribution factors, calculated the fixed end forces, consolidated them in a worksheet, and began iteratively applying the moment distribution method. Once we reached the point where the unbalanced moment, the amount that we were transferring by carryover, was less than about 1% of the initial fixed end moments, I decided that was sufficient, and we stopped and we found the moments in the frame by summing the quantities in each individual column. We then use those internal moments to find the support reactions and internal shears at A, B, C, and D. We compared these vertical reaction results with the approximate analysis results and concluded that they were reasonable. And we then constructed the shear and moment diagrams by integration. Well done.